Hello, my name is Kyuri from Seoul National University. In this video, I would introduce our work, Controllable Text-to-Image Synthesis for Multi-Modality MR Images. Healthcare is a multifaceted field that contains data from various sources such as image, health record genomics, and more. Recent studies like MatPalm from Google have showcased remarkable generative capabilities which have producing the answers from the given language questions. And various studies in medical applications using neural network aim to utilize multi-data sets for the fluent information. However, despite this advancement, medical datasets often heavily depend on open datasets, which include image data and corresponding radiological reports. As a result, owing the availability of public report datasets like MIMIC, many studies are typically restricted to specified modalities such as chest X-rays. Motivated by these considerations, our study aimed to explore how to controllably generate magnetic resonance images from text using diffusion model. To achieve this objective, we composed input sentences using key informations, MR images, and structural mask with the goal of producing sequence of diverse MR series. Additionally, an analysis of activation area was conducted through a visualization of attention map. Originated from the latent diffusion model, this framework incorporates several key components: CLIP as a pre-trained language model, a diffusion-based prompt-conditional generator, and an autoencoder. Additionally, it features a guidance denoising network designed to annotate a mask, which ensure the preservation of fixed organ structure information. As described in A, model training involves the input of image text and the structure mask provided by the annotator. These elements are integrated in the reverse diffusion process. In practical terms, the model is progressively denoising images within the latent space. The objective of the entire model can be formally defined as following equations, incorporating various of time step, noise image, text condition, and the structure mask. Furthermore, for multimodal image synthesis, the model is capable for generating image based on the text corresponding to which MR modalities. During the sampling phases, latent vectors are initialized with random noise and then conditioned by the text prompt. By fixing the initial seed and the structure conditions, while varying the modality text prompt, the model is capable of generating a sequence of multimodal images. To incorporate structure guidance inspired by ControlNet involves the guidance unit initially duplicating the parameter of the primary unit and permitting updates via structure mask. The clone parameter of the encoder are activated and interconnected through zero initialization convolution layer, referred to as zero convolutions. The input feature map is updated from zero initializations by incorporating the given additional conditions. Furthermore, to interpret text token conditions, we focus on spatial attention map using QWERTY and key and cross attention layer. The cross attention map for main unit are upscaled to match to the fixed image size. These arrays are then aggregated to corresponding to the given key with a word from the prompt, normalized and visualized as a heat map H, corresponding to the individual word token. The dataset utilized for this study is from a medical center, focusing on brain MR imaging of glioma tumors with 4 distinctive modalities: FLAIR, T1, Enhanced T1, and T2. Each dataset is accompanied by the diagnosis report that identifies the presence or absence of IDH mutations. These mutations are categorized as either mutant or wild type. To standardize sentence templates, a blank modality MR image type of blank glioma were used with placeholders for modalities and IDH type precises. In the evaluations of the synthetic image, FID was calculated to gauge image quality and diversity, while structure similarity index, normalized mutual informations, and normalized cross-correlations were used to measure the structure similarity across the MR series. The FID scores were found to be comparable to those achieved by alternative approaches such as Sung-Joon and LDM. Additionally, the correspondence of multi-modality slide sequence was closely aligned with the ground truths, serving as upper bound, while lower bound used random sequences. The clip score was also used to evaluate the correlations between clip text and image embeddings. Upon comparing the full prompt, modality only, and IDH only subset, the highest level of agreement was observed for full prompts. The Turing task for qualitative evaluation is structured into two distinctive types. Type 1 involves comparative analysis with a random pair of real and synthetic images from the same modality and to identifying the synthetic cases. Type 2 entails a qualitative assessment where experts rate a sequence of generated MR image on a 0 to 5 scale, with also considering whether the sequence represents the appearance of the tumor with an IDH mutant-like or wild-like phenotype. Experts evaluate 20 items per type, with the evaluation capped at 30 minutes. The results were affirmed by clinician reviewers to be highly qualitative, reflecting the characteristic of the input prompt has achieved. Therefore, the output results are shown as follows. Visualization of the attention map displays text element corresponding to synthetic outcomes. Along the y-axis, the map displays results of various MR modalities, including FLAIR T1, T1CE, and T2. Meanwhile, the x-axis arranges the world derived from the input prompt in order. The cross-attention layer emerged as a key factor in determining the attributions between text and image for each word. Activation map for mutant or wild for each sequence were averaged to obtain an average tumor heat map. Lastly, using t-SNE, comparative analysis was conducted for full MR images and average tumor attention maps. Tumor features are often having complex and overlapping characteristics. However, the selectively activated attention map demonstrates significant separations in the results. This distinct separation in the reduced dimensional space served to validate that the synthetic process has indeed produced conditionally appropriate outcomes, and further indicates that it could be an efficient approach for extracting desired feature informations. The framework proposed has demonstrated its capability to generate synthetic multimodal MR sequences. The sequences are guided by specific input conditions and leverage the diffusion-based denoising network. Furthermore, the analysis of cross-attention map aids the disentanglement in intrinsic feature within the generated images. Thanks for your attention.